In this video, we're going to look at a new topic that we need to cover at higher level. Now, up to this point, one of the key topics that we've covered was the new topic we introduced called differentiation, where we started to look at rates of change of function and calculating derivatives of it. What we're going to introduce in this video is a topic called integration. Now, integration is the opposite of differentiation. Integration goes the opposite direction to it. Now, it could be used for several different things. What we're going to do in this video is look at the basic premise of how we differentiate simple terms, and then we'll build up to what they can be used for. Now, when you're integrating something, these are the key rules you have to follow. Now, if we have something f dash of x, which was our derivative or derived function, to calculate the integral of it and get back to our original function, this is the notation that we have to use. So f dash of x equals this. Now this symbol here, what looks like a large S, is actually our symbol for integral. So what this means is f of x equals the integral of f dash of x, our derivative, dx. Now the dx part here tells us the variable with which we are integrating with respect to. Now we know f dash of x is some sort of function or equation that has a dependence on x, i.e. the variable in it, the key variable we're looking at, is x. Well, what this means is that is the variable we're integrating with respect to. Now, at higher level, what we're going to look at is integrating single variable functions, single variable expressions. But this isn't always the case. So when you go above higher level, you might look at equations where there's more than one variable. And for these equations where there is more than one variable, we need to know which one to differentiate with respect to. And that's what this wee dx part here tells us to do. Now, the two simple terms we're going to look at in this video is when we've got a term that's of the form x to the n, so x to some power, and when we've got a derivative form where it's ax to the n, where a is just some constant or coefficient. So something like x cubed, 6x squared, that sort of thing. That's what we're going to look at integrating. Now, when we're doing it, if we have something that's just of the form ax to the n, when we find the integral of it, we get something that looks like this. We get ax to the n plus 1, so we've raised the power by 1. We then divide by this new power, by this n plus 1 here. Now you'll notice we've got a plus c here at the end. I'm going to talk to you about that in just a second. If we were to do the ax to the n, same sort of thing. The x goes to the n plus 1. We then divide by this new power. The a doesn't do anything. A is just a coefficient. There's no dependence on x at this point. So we just leave it where it is. We then add on a plus c. Now, for both of these, that c has the same sort of thing. That c means the constant of integration. Now, when we do an integration, or an integral, we will end up with a constant of integration at the end. Now, in some cases, we'll end up with just a plus c left. So it's just a generic constant, we don't know the value of it. Other cases, we will be given conditions where we are able to calculate that. We're able to figure out what this value of c is. What we're going to focus on here is just getting the basics of it. I want you to always remember to write a plus c. Now, the reason we write this is if you were to work back the way for this and take the derivative of f of x to get back to f dash to x, taking the derivative of ax to the n plus 1 over n plus 1 or x to the n plus 1 over n plus 1 will give you this original part of the expression here. But remember, the plus c is a constant, so it's just a number. It's a 3, a 6, a 10, whatever. If we were to take the derivative of that, it would become 0. So there'd be nothing there just as there is here. But we have to take into account that there could have been something there in the original function, which is why we always must include the plus c. Now this is a key thing. You have to make sure you do that, especially when it's exam style questions. You'll lose marks if you don't. And the last thing we want is that costing us marks that could go from an A to a B or a B to a C. We don't want that at all. So let's look at a couple of examples of how we integrate functions. So let's imagine this first question here. If the derivative f dash of x equals x to the power of 4, find f of x. So we're taking the derivative and we want the original function. So we need to integrate. So we know that f of x equals the integral of f dash of x, our derivative, dx with respect to x. So what we do, to start with, we have to substitute in. We have to know what we're integrating and what we're going to do. So we have to say x to the 4 dx. So I want to integrate the x to the 4. So now I just follow the simple rules we talked about on the previous slide. So I keep the x, I raise the power by 1, so it goes to 5. I then divide by this new power here. So I get x to the power of 5 over 5. But here is the key step. Remember to include the plus c. There is a constant of integration there. We don't have conditions to find it, so we don't know what actual value it takes, but there could be a value there. So we have to take that into account. So it's x to the power of 5 over 5 plus c. Do not forget to include that. And if we have a constant in front of the x term, well, then that's just the same set of steps. We know our f of x is the integral of f dashed of x dx. The only difference being is that this time, our f dashed of x equals 6x to the power of 5 dx. It's just a different function, and there's just a constant term, a coefficient of our x to the power. So we still follow the same steps. So we start by putting our x and raising the power, so it becomes to the power of 6, and we divide by this new power, but we have to make sure we put the coefficient in front. So it's actually 6x to the power of 6 divided by 6, and then plus c, plus our constant of integration. We then simplify if we can. Well, 6x to 6 divided by 6, 6 divided by 6 is 1. That just gives me x to the power of 6 plus c, my constant of integration. So calculating the integral of a simple term like this is actually quite straightforward. And when we get more complex terms, so ones involving roots or fractions, it is actually still fairly straightforward. We just have to remember what our first step was when we were finding the derivative, and that's put it into a form which we can differentiate. So let's look at this example here. Imagine my derivative f dashed of x equals 1 over the square root of x, and I want to find the original function f of x. Well, the first thing you have to do is take this function and make it something you can calculate the integral of. So we get rid of the root, so I'd say f dashed of x equals 1 over x to the power of a half. We then have to bring it all up because remember, we always want it written in this form, x to the power of n. This isn't quite there, so we have to bring it up and make it x to the power. Now it would be x to the half, but remember it's on the bottom, so it's actually x to the negative a half. Now that we've got it ready, we can calculate our original function f of x. We know f of x is equal to the integral of our f dashed of x dx, so f of dashed of x with respect to x. We substitute this in. So it's the integral of x to the negative a half dx. What we then do is we follow the exact same steps as we did before. Take our x, raise the power by 1, so negative a half plus 1 gives me a half. We divide by this new power, so we divide by the half. And we then add on our constant of integration. If there was a coefficient here of x, this would stay on the top as well. But there's not, so we just leave it. We then sort it into a functional form. Well, dividing by a half, that's the same as multiplying by 2. So it's 2, and x to the half can be written as the square root. So it's 2 times the root of x plus c, my constant of integration. And that's it, finished and done. If you ever wanted to check any of these, take your function and calculate the derivative. You should get back to this form here at the start. We just have to remember that. So get it in a form we can take the integral of the same way we would for a derivative. It's just going the other way. Now, if we've got more than one term, it's still actually fairly straightforward. The only thing we have to remember is the same thing we remembered when we were calculating the derivative, which is do each term on its own, one at a time. So for example, if I had the integral of f of x plus g of x dx, I would split it and do integral of f of x dx, so the first term, plus the integral of g of x dx, the second term. And if I had more, I'd just add on even more. So an example of this, find the integral of f dashed of x equals 3x squared minus 1 over x squared plus 7. Now first thing to check, is it in its form where we can calculate the integral? First term is, third term is, middle term isn't, so we've got to fix that. So first thing we have to say is, right, f dashed of x equals, well, keep the 3x squared, 1 over x squared becomes minus x to the negative 2, then plus the 7. And then it's just a case of calculating your f of x, which is the integral of that. So f of x is the integral of 3x squared, take away x minus 2, plus 7 dx. And to do this, follow this rule. Split it up and do each term individually. So we do integral of 3x squared dx, take away the integral of x to the negative 2 dx, plus the integral of 7 dx. And once we've done each of those on its own, we've then got our final answer. So we know then f of x equals, well, integral of 3x squared raised to the power by 1 becomes a 3, divided by the new power. It's then take away x to the negative 2 raised to the power by 1, so it becomes x to the negative 1, divided by the new power over negative 1. And then this last one is plus the integral of 7. Well, remember, 7 on its own as a constant is the same as 7 times x to the 0. So if you're integrating a constant, it simply becomes that constant times an x. And we then have to include the plus c, or constant of integration. Now, we don't include one for each of them, we just include one generic one at the end of the calculation for multiple terms. We then simplify everything out. So f of x equals, well, 3 over 3 gives me 1, so I just get x cubed. This is minus and minus, so that becomes a plus, and x to the negative 1 becomes 1 over x, then plus my 7x, and then plus my constant of integration c. So that there is my final answer. When we're integrating multiple terms, we just have to remember and do that. Break it up, each term individually, and get an answer at the end. Don't ever forget this plus c. If we've got limits or if we've got conditions to find it, great, do it. But if it's just a generic integration like this, do not forget that plus c.